So we're going to get started. Our speaker today is Wen-Chen Liu, and he received the BA and MS degrees in electrical engineering from National Chung Kung University in Taiwan in 2010 and 2013, respectively. He is currently working toward the PhD degree in the Department of Electrical and Computer Engineering here at the University of Illinois. His research interests include integrated circuit design for power converters with high performance, high power density, and high conversion ratio.
Do I need to use that? No. Okay. Hello everyone. My name is Wen-Chen Liu. So we are the team from University of Illinois Urbana-Champaign, and this will be presented in San Francisco next week. Today I'm going to talk about hybrid Dickson switched-capacitor DC-DC converter. That's on chip. So first of all, let's look at this example. The input is lithium-ion battery with the voltage range from 3 volt to 4.5 volt. And the output is either wearable or portable device, which is commonly operated at 1 volt. And some of the application will be operated at subthreshold region, which can be down to 0.3 volt. So what kind of power converter do we need in this application? So first of all, we want it to be high conversion ratio up to 15. Also, we want it to be smaller, and we want the output current to be high enough. So that's high current or power density. Of course, we want it to be high efficiency so that we can lengthen the lithium-ion battery lifetime. We want these performance to be good at wide range voltage regulation. So how can we compare our work to other works? We have talked about efficiency, current density, and conversion ratio. So first, we have a plot of efficiency versus conversion ratio. We also have current density versus conversion ratio. If we can achieve both the goals 1 and 2, that means the efficiency is high at high conversion ratio and the current density is high at high conversion ratio. So how about a conventional switch capacitor can do? For typical conventional switch capacitor converter, it can achieve goal one at some discrete conversion ratio, only at some fixed conversion ratio. But some of the good works in the past, they address this problem by using multiple stages so that they have multiple points at this point for goal 1. But that means they try to use more chip area to achieve goal 1, but at the sacrifice of goal 2. But how about conventional buck converter? Let's look at the schematic. Both of the switches have to block input voltage. This input voltage is higher than the output voltage. This is the nature of the buck converter. And because of this, these switches have to block higher voltage. That means they will have higher RDS on if we choose higher voltage rating device or switches. This also means it's hard for conventional buck converter to achieve both goals 1 and 2. So we come up with this idea, hybrid switch capacitor converter. This is the conventional switch capacitor converter. It has been proved that in many papers, so this is one of the good examples, it has been proved that conventional switch capacitor converter can have high conversion ratio with high efficiency. But its application is limited at low current because of the charge redistribution loss. As you can see here in this waveform, the blue line represents the convention represents the capacitor current for a conventional switch capacitor current, converter. As you can see, there is a spiky current. That means the RMS current for this case is higher. By adding a small inductor, hybrid switch capacitor converter can eliminate the charge redistribution loss. And so we can achieve smooth capacitor current. This will help reduce the charge redistribution loss and lower the output impedance. Let's look at this. Let's look at this plot. This plot is output impedance versus switching frequency. Because there is no more charge redistribution loss, we can see this. Hybrid switch capacitor converter has low output impedance when the switching frequency decreases compared to the conventional switch capacitor converter. What does it mean? It means that we can either have larger capacitor voltage ripple, or we can have smaller capacitor value. The most important thing is that we can lower the switching frequency to reduce the switching loss, and at the same time we have low enough output impedance. That's why we can improve the efficiency of the conventional switch capacitor converter. Kevin? So this is how we implement the whole system. We have chosen Dickson converter as the switch capacitor converter structure. We have 8 power MOSFET, all these red power MOSFETs. We have 3 flying capacitors, 1 output capacitor, and 1 inductor to form hybrid switching capacitor converter. In this system, we also integrate gate driver, level shifter, output voltage regulation, and capacitor balancing. These passive, including capacitors, all these capacitors, and this inductor, are packaged using this method in order to increase the current density. So this die is in wafer level flip chip package. By using a high density interposer, we package the passive and the die together in order to increase the current density or to lower the whole area. To increase the current density, we can do more. First of all, we can reduce the capacitor area used by the gate driver. So for conventional bootstrap gate driver, we definitely need to use a bootstrap capacitor, CB, to temporarily store the energy to drive the power MOSFET to turn it on. However, if you want to have high enough VGS when CB is connected to CGS, we want CB, the bootstrap capacitor, to be high enough so that there is no too much voltage drop, because there is charge sharing when CB and CGS are connected. However, if we try to increase this capacitor area, that means we're going to lower the performance on current density. And at the same time, we don't want this to be too low that will increase RDS on per area of this MOSFET, and that will decrease the efficiency of the whole system. So we have employed a technique of voltage borrowing. How are we going to do that? As you can see, we have V1, V2, V3. These are the existing flying capacitor. And these blocks, triangle blocks, these are our gate drivers. As you can see, these gate drivers are driven by the existing flying capacitor. For example, V3 is the positive terminal of C3. It also powers the gate drivers for M7, as you can see the connection here, gate driver for M6. Also, V2 is the positive terminal of C2, and that powers the gate drivers for M8, M5, and M4. And because V1, V2, and V3, they are changing, we also consider this issue. So let's look at this example of M8, the gate driver for M8. So the supply voltage for this gate driver is Vin and V2. V2 is changing, Vin is constant. So that's why we get this. Vin minus V2 will be the supply voltage to this gate driver. We want to see when we need to turn on the this power MOSFET M8, will that voltage high enough to turn the power MOSFET on? So we also consider this in our circuit design. So when M8 is supposed to turn on, the supply voltage to that gate driver is high enough to turn this on, so that the RDS on this MOSFET is lower. So there is another contribution for this work. Ringing reduction, voltage ringing. If we have too fast transition, switching transition, we will have large ringing. But what if we use too slow switching transition? Let's look at this example. If we use only weak gate driver, we're going to see this. This is the VGS waveform. The VGS is increased at very slow rate. That means the RDS on is high at this region. So we come up with this idea. Segmented gate driver. We combine weak driver and strong gate driver at the same time. So how are we going to do this? At the beginning of the switching, we use a weak gate driver to turn on the power MOSFET so that we can reduce the voltage ringing. But we don't want the RDS on at this region too high. So after IDS is fully conducted, we turn on the fast gate driver, the strong gate driver, so that VGS will be raised at a faster rate. So in this case, we're going to have less RDS on in this region. So the segmented gate driver reduces the ringing without sacrifice of the efficiency, the whole efficiency. This is how we implement the whole system. This is the chip or the die. It is implemented by using 65 nanometer box CMOS process with the area of 4 millimeter square. And the blocks labeled M1 through M8 include the power MOSFET, level shifter, and gate driver. We have also integrated some controllers, some I/O drivers on this chip. So we first measure that with a low profile inductor with 180 nanohenry inductance, 24 milliohm DCR. We have tested with different output voltage, and we measure that the peak output current is 1.53 amp. And we also move on to test with larger inductance, 470 nanohenry with 8 milliohm DCR. In this case, we achieved the peak efficiency of 94.2 efficiency. So at the beginning, we have talked about efficiency, conversion ratio, and current density. So we are going to compare the performance with other prior art. So in this plot, the blue shade it represents this work. We also compare that to a conventional buck converter, a conventional switch capacitor converter, and two hybrid switching converter. So as you can see, the conventional buck converter has low conversion ratio but higher efficiency. How about the switch capacitor converter? It has higher conversion ratio but at lower peak efficiency. These two hybrid switching converter, they have one of them has pretty good efficiency, but limited at lower conversion ratio. This is our work. We achieve goal 1, which means higher peak efficiency at higher conversion ratio. We have also compared the current density versus conversion ratio. This work still it achieves pretty good current density, but at lower conversion ratio. Other works have lower current density and lower conversion ratio. We achieve goal 2 with high peak current density at high conversion ratio. So here's the conclusion. We have done the first CMOS implementation of a hybrid Dickson switch capacitor converter, which has high power density and efficiency for high step-down voltage conversion ratio, which is good for low voltage loads like wearable device, portable device, which are powered by lithium-ion batteries. In this work, we have done two contributions. One is capacitor area reduction by using the voltage barring technique. The second contribution is the ring reduction without sacrifice of efficiency by using segmented gate driver. So we want to thank U.S. Army Research Lab, Texas Instruments, and Sonic. So that concludes my presentation. I am happy to answer any question if you might have.
I don't have another question. How do we know about the Plato voltage? Like, how did we determine what was the value of Plato voltage between the feedback?
Sorry. The Plato voltage is actually sensed by this. It's sensed by this inverter. So because we use the same technology for this gate driver as well as this low skew inverter, so we can use this to sense the Plato voltage. So that
is the changing voltage on the gate drivers putting this operation at risk? For example, for M8 and for M5, where you don't have a stable voltage on gate drivers, is there switching? Does it harm the mechanism of false activation of this feedback?
which one? M5, M8?
Yeah.
Yeah, we can talk about that.
Yeah.
Yeah.
So for M8, in the previous slide, so M8 and 7 are PMOS. Right?
Yes.
So in terms of gate driving, like why do you use PMOS for 7 and 8, and how? Can you explain again, like how you? So if you want to turn on M8, then you want to have a low, you want to have lower gate drive voltage, right?
Mm-hmm.
So which means the point you made was like you want to turn on M8, then you have to supply the current. Is that correct? Is that what you said?
Mm-hmm. Okay.
So in that case, it will be you want to turn off.
Yes. So turn off is definitely fine, but if you want to turn that on, that would be a issue. So we consider that here. So let me repeat his question. His question is why do we need to choose PMOS for M7 and M8, and how are we gonna turn on M7 and M8? So for the first question is that if we want to have MMOS here, whenever we need to drive an MMOS, that means we need a voltage higher than the source voltage. So if we want to, for example, if Vn is 4 volt, and we need 1 volt more than this to drive that MMOS, that means we need to create another voltage to drive that MOSFET. And then we will go back to this situation. The conventional bootstrap gate driver. And how are we going to turn on this? That means we need to choose a voltage that's lower than Vin in order to turn this on, right? So that's why we can either choose V3 or V2 or V1. There are several choices here. But V2 can turn this on with high enough voltage, but within the voltage rating of this MOSFET.
You mean the gate voltage?
That's right. VGS or VGD. Mm-hmm.
So this voltage borrowing stuff, how does this work on like startup? Because the startup of the converter seems like you don't have any voltage, and then what do you do?
Yeah, that's a very good question. So his question is, how are we gonna start up this whole circuit? Because if we don't have the voltage at V2, V1, or V3, these gate driver will not turn on correctly. So our solution for now is that we have a pre-charged circuit externally for this time. So whenever we need to start up the whole circuit, we have to charge C2, C1, C3 with enough voltage, and then we turn that on afterwards.
Okay. Does draining current from the flight capacitor to drive the gate drivers have any effect on the capacitor voltage balance?
Yes, that affects some. But so far, for our measurement, yeah, it was not observed in our measurement. It should affect some of the measurement because, for example, V2, 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 there are actually 1, 2, 3. They are using the energy from C2. But for M6 and for V3, it only provides power to M6 and M7. So it's gonna be some unbalanced issue there. But so far in our measurement, we haven't observed that.
This is my first time listening to you, so I want to clarify some ideas here. So the main contribution of the research is not really the hybrid quality, it's more of the gate driver design, right? Or voltage boring technique instead of stroke. So I have a question like, what is the trade-off between this new voltage boring technique versus traditional?
Okay.
Especially like the baptism.
Mm-hmm. So his question is what's the trade-off using our developed techniques like voltage barring technique as well as the segmented gate driver. Let's first look at this. As you can see, if we want to include another circuit like the strong gate driver here, that means we need more area for that. That's the overhead using this technique, the segmented gate driver. So, and this is the, if we want to use this technique, we're gonna increase a bit on the chip area. That's for this technique. For this voltage borrowing technique, the big issue for this is that Vin is changing. If Vin is too low, that means we're gonna have lower V2, lower V3. The most important point here is that, for example, if Vin, V2 are both lower, that means Vin minus V2 is lower too. That also means the voltage supplied to the voltage to drive the power MOSFET is lower, or the VGS is lower, or the RDS on is higher, so that the efficiency is higher too. But in our case, if we use a more constant battery voltage, this will be similar. This voltage should be similar, and this is specifically designed for this input voltage, and that would be fine.
Are the losses which are led by lower voltage on the input, which causes higher RDS on the switches, justified in your optimization in terms of removing the bootstrap capacitor and getting better density?
Would you mind to repeat that?
So you have this option of having a dynamic input voltage, but the downside is your gate drivers are supplied by the same source. So the RDS on will increase, at the same time your efficiency will go down. But looking at the project overall, that's your optimization.
Which project overall?
This whole thing.
Okay.
Overall. Using this technique, is this just does this have enough justification such that you don't use bootstraps, but in turn you get a much better density and efficiency at the same time?
Okay.
So can you like say this is optimized even at the gate at having those losses, but negate something even better?
We won't say. I won't say this is the optimized solution, but let's look at this. When we use the bootstrap gate driver, we definitely need to use a bootstrap capacitor. That's an extra capacitor in this case. And how does this capacitor look like? Let's say if we want to have a bootstrap capacitor that's 10 times of the CGS, and the background is that the largest capacitance density on chip is actually formed by a MOSFET. So if we want to use a really large capacitance on chip, that means if we want to have a 1x unit of MOSFET, and we use the conventional bootstrap gate driver, we're going to use 10 times capacitor area for driving this. So this definitely increased a lot on the whole chip area. But for the accurate value of how this compare, how are these compare, that's what we are working on.
So you are using all-chip capacitors, and what's your switching frequency?
Yeah, that's a good question. So for this case, we have used 500 kilohertz for the switching frequency. But because this is a, let's look at the, because of this structure, the equivalent switching frequency at this inductor is twice. So the equivalent switching frequency as seen by this inductor will be 1 megahertz. And at this node, the voltage is lower than the input voltage. That's why this inductor is lower than the conventional buck converter. And for the capacitor, that's also a good point because for now we have it external. We have it external, but in the future, if we push it to higher switching frequency, we might have everything on chip. But so far, we use this interposer to co-package them. And this is also designed for high current. So that's why we have the capacitor outside the chip. Because for those capacitors inside the chip, we have to also consider some bottom plate capacitance losses.
Cool. Well, let's thank our speaker again. Before Matt gets